So the next concept that we need to understand is shear versus bending. So let's say we have a beam, right? We have a beam here, and this beam, if we put a force at this point in the beam, this beam could be made of anything. It could be made of like concrete, could be made of steel, could be made of timber, could be made of anything, could be made of anything. So all we need to know is we can put a force at any point in this beam. And if we can keep increasing this force, right? We keep increasing this force, keep pushing down, there's going to be a point where this beam will fail, right? This beam will fail. It'll crack or it will bend. Depending on the material and dimensions, there's going to be a max limit for the amount of force that we can put on a beam, right? And the two ways that we're going to look at where it can fail is shear and bending. So shear failure occurs when, say for example, this is our beam, and if we're looking at this section here, and we can have one side of this section of the beam experiencing a downward force and one side of this section experiencing an upward force. And if this force is too great, like this difference in force, then we can have a failure here at this point. We can also have a beam fail in bending. So we might have the force here acting here, and this beam can bend, or it's going to bend and deform. So depending on the material, it will keep bending and bending and bending until it gets to a point where it can't recover its shape, and it'll fail. Just like if you have a fork or a spoon, and if you bend this spoon, you might put a force there and a force there, so when it starts bending in this way, if you put a little bit of force, you might bend it and it will recover its shape and it will return to its original shape. But if you continue to bend it, right, if you continue to put more and more force here, and it will bend, and then it will reach a point where it will no longer recover its original shape. It's going to bend until it fails, right? And if you keep bending it, it's going to eventually snap, or it's going to break, right? You'll have two parts of the spoon, right? So these are the two ways that we're going to look at that the beam can fail. We can draw diagrams to represent where along the beam we're going to experience the highest shear force and where we're going to experience the highest bending moments. So if we look at this symmetrical beam, most likely the highest bending moment is going to be in the middle, and the highest shear force for this example can be anywhere along the beam is going to be almost identical, right? We're going to have high shear force values throughout the beam. So every beam is different, and every beam needs to be analyzed, and we need to put a number on what these values are. All right, so let's have a look at two almost identical beam examples. One beam has a 10 kilonewton force here, and the other beam has a distributed load of 2 kilonewtons per meter here, right? And let's say this beam is 5 meters long. This beam is 5 meters long. And we're assuming that this is halfway along the beam, so this will be 2.5 meters. Because this beam is symmetrical, we're going to have 5 kilonewtons, right? 5 kilonewtons acting here. We can say that it's going to be 5 kilonewtons, and we're going to have 5 kilonewtons here, right? It's going to distribute to the supports evenly. And here, we're going to have, just quickly, we're going to have 2 kilonewtons. This should be 2 kilonewtons per meter. We have 5 meters, so the total force is going to be 2 times 5, 10 kilonewtons. So we're going to have 10 kilonewtons, and it will be acting halfway along the beam. So 10 kilonewtons. So 5 will come here and 5 kilonewtons will come here. Okay. So we have very similar beams, but one is a point load, acting at a single point in the middle of the beam, and the other one is a distributed load acting throughout the beam. All right. So what we can do is we can draw our diagrams. Now we've found our reactions, and we can extend like this along the beam. We can extend like this and project this beam to a diagram. So this will be our shear force diagram, and here we have our positive and our negative side, right? So how we can draw it, we have 5 kilonewtons going up. We can say this is positive 5 kilonewtons, and we don't have any forces until we get to this 10 kilonewtons here, right? We don't have any forces until we get to 10. So this will be constant until we reach this midpoint, and it will be 10 kilonewtons down 10. So at this point will be negative 5 kilonewtons, and then we go across and we reach our 5 kilonewtons again, and we'll go up. So the constant shear of 5 kilonewtons throughout the beam. So if we look at our other example, we have a very similar thing. It goes up to 5 kilonewtons here, but we have a 2 kilonewtons per meter distributed load throughout the beam. So for every meter we move across, right? So say we divide this into 5 meters. For every meter we move across, the shear value of this beam will decrease by 2 kilonewtons, right? So we're eventually going to get to the middle and it should reach 0. We can go to the middle and across, and then this will be -5 kilonewtons here, and we will return back to 0 at the end of the beam, right? That's our shear force diagram. And now we can draw our bending moment diagram. So we can extend this further and we can draw our bending moment diagram. So how we can find our bending moment diagram is from our shear force diagram. So the area of our shear force is going to be our bending moment, right? So these two rectangles and these two triangles. So the area is 5 times 2.5, right? This is 2.5 meters. So this is just 5 kilonewtons times 2.5 meters, right? The area is 12.5 kilonewton meters, right? So because this is a constant throughout, we're going to have, and it's a positive, and it's a constant throughout. There's no change in our shear value. It's just going to increase linearly until we reach the middle, And then, because it's a symmetrical shear force, we're going to have the exact same happening on the other side. So it's going to decrease because this is the negative side, right? This is the positive side. So on the positive side, our bending moment is going to increase, and on the negative side, it's going to decrease. And it will decrease linearly because we don't have a changing shear force value. All right, so if we look at our triangle here, area is equal to half the base, right? So the base is here, which is 2.5 meters, times 2.5 times the height, right? So 5 kilonewtons, right? So the area is going to be 6.25 kilonewton meters. All right, so we know that this one is 12.5 kilonewton meters. So on this side, because we have a positive triangle, so it's going to be going in this direction. But we have a decreasing shear force, right? The shear force is decreasing. So that means that it's going to be like a parabola. It's going to decrease. As we reach 0, there's going to be a point where it will be parallel to our axis, right? And this point, it will be 6.25 kilonewton meters. Because we have a symmetrical, we can just see that it's going to decrease and be identical on this side. So for our first beam, we can see that the shear failure could occur anywhere along this beam, right? Anywhere, because the shear force is high, or you can say it's at its maximum throughout the entire beam. There's not a point in this beam where it's lower than the other, so it can occur anywhere. Whereas with our second beam, most likely the shear failures will occur at the ends, right? Most likely, because the shear force is highest at the ends, right? The shear force is the highest at the end. So these beams will differ. One beam will have a chance of failing high at the ends, and the other one could fail anywhere throughout the beam. So if we look at our bending moment, they're both high at the midsection of the beam, right? They're both high at the midsection. That's where the maximum bending moment is. But one has a much higher bending moment. One has double the bending moment of the other beam. Okay, so bending failure is most likely to occur in the middle of both beams. This is just a general idea of what the shear force diagram and bending moment diagrams are and how you can use them to analyze a beam.